Hey everybody, Mr. Plantt here, and today we are going over our Unit 2 study guide. Now this is very similar to the last one, just remember that I'm not writing out every single answer for you, but I am discussing all the answers. So if you're listening and you're taking in what I say and you're adding it to what you've already done on your study guide, you are going to have an awesome study guide. Alright, so we have some different sections, right? We have these kind of bolded things are there so that you can see all the different sections within the study guide, which are kind of the major topics in our test. Okay, so the first one is define a chemical property. Now, a chemical property is a little different than a chemical change, but they are related. A chemical property is one where to observe that property, there has to be a change in the chemical structure of the substance. Okay, and so on the other note, sorry, the big idea is change in substance, right? The property is observed when there's a change in the substance. The physical property is one where we can observe it without a change in the substance, right? Without that, right? So we don't need that. Some examples of chemical properties are things like reactivity with oxygen and air, or combustibility when mixed with another chemical, or the reactivity with other different types of elements out there. Right, those are all chemical properties. Chemical properties are a little bit harder to wrap our brain around, but if you just think about properties that result in the change in a substance, it'll be a chemical property. A physical property, on the other hand, is something that only affects the physical appearance of the substance but doesn't change the substance at all. So something like color. Right? Color doesn't change the actual substance, but it does change the physical appearance of it. Other things are stuff like density. Density is just, you can change your density by changing how much of the substance you have. And so the substance doesn't change itself, but the density does. Even things like malleability, how easy it is to bend the material, that's a physical property because it doesn't actually change the substance. Okay, so on the very related note, what is a chemical change? Well, a chemical change is a change that results in a new substance. Okay, so it results in a new substance. So that, my classic example is always the burning a piece of wood, right? If we burned a piece of wood, right, here's my log, woo, right, and if we are burning it, then we're going to end up with a material called ash. Now, ash is different than wood. It's a new substance, so that's a chemical change. Right, so a chemical change is a change that results in a new substance. How can you tell if you've undergone a chemical change? Well, that's the getting a new substance, right? If you have a new substance, one that you didn't start with, and one that is chemically different, that's a chemical change. So some examples, like my picture above, right? Burning a piece of wood. Also from the lab we just did, mixing calcium chloride with baking soda and water. Right? Remember that reaction created heat and gas, so that was evidence of a chemical change. And then even something like ones where you get a color change, but it's unexpected. So like putting iodine in with, excuse me, putting iodine in with cornstarch. Right? That we expected it to, okay, maybe it gets a little more brown, and then it turns this black purple color. That's unexpected. That's a chemical change. All right. Physical change, the one I really like to point out is like starting with an ice cube. Well, that's a horrible cube. And it melting, right? So ice cube melting is a physical change. That's an example of one. And, oh, this should say, oops, that should say physical. Right? But a physical change is just a change in the appearance, the size, the shape, or the phase of an object. So how can we tell if it's undergone a physical change? Well, the size had to change, the color could change, the phase, so it should have gone from solid to liquid, liquid to gas, gas to solid, solid to gas, whatever way you want to bounce around. But the big thing is it's still the same substance. So even if we melt an ice cube, it's still water. It's not a new substance, it's still water. And so some examples of that, right, melting the ice cube is one, tearing a piece of paper in half, right? It's still paper, but now it's smaller. That's a physical change. Or even like hammering metal, right? Denting that metal, that's just a physical change because we're changing the outward appearance, but not the actual chemical structure of it. All right, the periodic table is our next big group. So, what are periods on the periodic table? Well, if I draw a really bad representation, oh my goodness, really bad representation of the periodic table, right? And it's not drawn to scale by any means. Okay, the periods on the periodic table are the rows. Oops, so let's go back. Let's do it this way. Right, the rows are the periods. Okay, so they're the rows. And that means that our groups then are going to be our columns. Right? Our columns on the periodic table are called groups, so that when we're looking for groups, we're looking vertically, and we're looking for periods, we're looking horizontally, going left to right for periods, going up and down for groups. Okay, so what group numbers or elements are associated with the following group names? All right, I'm not going to do a big picture of this one. This one we had notes on, but they were on your own. It was one of those lessons where it was like, hey, you need to do these 3 things, and so you should have got these. And so I'm just going to talk about them without drawing too much. And if you didn't get them, you can either go back to those notes or even just Google a image of the periodic table that's color-coded so you can figure out these. The alkali earth metals, those are our first group. So group 1A, those are our alkali earth metals, followed closely by our alkaline earth metals, that's second group. Okay, so alkaline are group 2A, alkali are group 1A. This is a big, the difference between alkali and alkaline, that trips people up a lot. So you've got to be really careful about, is it alkali or alkaline? Because it's the difference between 1 and 2. Our transition metals are all those middle metals. So once the periodic table drops down, and after those first couple periods, you have the kind of drop down, and you have all those metals where like silver and titanium and palladium, all those metals. Those are all transition metals, those middle chunk metals. Transition metals. Okay, so they're like, I guess it'd be groups 3A through 12A. Okay, our other metals, this is where it gets a little funky and why up here I put or elements, because it's not necessarily group numbers anymore. Our other metals are, if you think about on the periodic table, we have this line, kind of stair-step line. Remember, everything to the left of it is a metal, everything to the right is a non-metal. Well, our other metals are the ones that end up being kind of right in this section of the, like right across that line. Right, those are our, to the left side of the line anyways, those are our other metals. Okay, and then excluding these last 2 columns, that's the big one, right? These last 2, and this is a horrible picture, but you'll get the idea when you pull up a image of the actual color-coded periodic table, or if you're looking at yours that we did in class. The ones to the left of the stair step are other metals, and then our non-metals are on the right side of the stair step, excluding these last 2 columns. The last 2 columns are technically other metals, but they're so special we give them specific names. Okay, so our halogens then are the second to last column, the second to last group, group 17A. Those are our halogens, and they're special because they are the ones that they react a lot because they only need 1 electron to fill their outer orbital. So they like to combine with other things. And then our last ones, the guys that have full electron orbitals, are the noble gases. That's group 18A, the very last column on the right side. Those are our noble gases. Okay, so you might have just heard me talking about a valence electron. So to mention this, I'm going to draw a quick picture. So let's say I have helium, for example. So I have 2 protons, 2 neutrons, and then out around it, in its outer shell, I have 2 electrons. Okay, valence electrons are the ones in the outermost shell. And so let's say instead of helium, oops, that's the wrong one. Instead of helium, I had lithium or whatever. I had another orbital. Well, now the valence electron would be this outermost guy, right? Whereas before it was those two that were in the outer shell. Now it's this outermost one. And this kind of ties into what is an orbital. Remember, an orbital is the area where we are most likely to find these electrons. Right? It's kind of these rings that we draw, where we know that it's easy to draw them in rings, but it's not accurate. They're actually in clouds around the nucleus, and so we call them orbitals. It's areas where the electrons orbit the nucleus. How many valence electrons do alkali earth metals have? Well, the way we can tell valence electrons is by what group the element is in. And so all the alkali earth metals are in group 1A, so they all have one valence electron. It's kind of part of the periodicity of the periodic table. The repeating pattern is that up and down they all have the same valence electrons. So on the same note, how many valence electrons do halogens have? Well, they're in group 17A, and the weird part about that is that we have to remember that if it's above 10, we have to subtract 10 off. If you think about the transition metals, there are those 10 in the middle group. We kind of ignore those because they hop around and do a couple weird things. And then when we get back up to our other metals and nonmetals, that's where we start counting again for our valence electrons. So halogens are in 17A, right, which transitions to 7 valence electrons. Right, because they're in that 17A minus 10 is 7 valence electrons. Which brings us to why is the last column on the periodic table called noble gases? Well, it has to do with their valence electrons. These gases in group 18A, so the far right column, they are all gases that have full outer shells. So they have a complete set of valence electrons. And because atoms, the way they react is by sharing or stealing or donating electrons. Well, if your outer shell is full, you don't want to do that, right? All elements want to get to a full outer shell, so they don't want to share anything, so they're nice and happy, and they don't want to react with anything. So we call them noble. They don't want to mingle with all the other elements, so they're above them, right? They're noble, they don't want to react. Yeah. Okay, atom identification. We spent a lot of time on this, so it should be pretty straightforward. So I'm going to go a little bit fast to keep this video from being too long for you guys. So an atom's atomic number, how can you find it? So I'm going to draw a little square here. And let's say I have carbon. So I have 6C 12.011. I might say carbon. And sometimes the name is above, right? The order of these change around a little bit. And so if we're looking for the atomic number, it might change on your periodic table, but on ours that I gave you guys, it is the number on top, right? Always the number on top. And whenever you have a new periodic table, you should always look for a key and see where they're telling you that. So if our atomic number tells us our number of protons, usually the whole number on the periodic table, and it's usually on top. Okay, so that means then our atomic mass, our atom's mass number, is this one. Remember, the reason it's a decimal on the periodic table is it is an average of all the isotopes. So when we're filling out our atom identification charts, we don't want to use the atomic mass on the periodic table if we don't have to. If we have protons and neutrons given and we can add them together to find that specific isotope's mass number, we want to use that. Right? We only use the average on the periodic table as a last resort. Okay, and then we have the C, that's the element symbol, so carbon for C, and then carbon, of course, they're at the element name. And some tables leave off the name just to make it nice and clean, but ours has it on there, so it's kind of nice. Okay, how can you find an atom's total charge? Total charge, remember I kind of made a nice equation for us, is protons minus electrons equals total charge. And the reason this works is because each proton is a positive 1 charge, each electron is a negative 1 charge. So if we take our positives and subtract off our negatives, we'll get, so say we have 9 protons and 8 electrons. Well, our total charge then is positive 1, because we have one more positive charge, one more proton than we do electrons. The thing to remember for this is that we always assume the total charge is 0 unless we are told otherwise. So unless a chart gives you numbers of protons and electrons and you can find the charge, or if it tells you the charge, then you can assume it's some sort of number. But if it doesn't give you protons and electrons or a way of finding protons and electrons, or if it doesn't just tell you the charge, always assume the charge is 0. And then if the charge is 0, we have the same number of protons and electrons. Okay, we're to this nice handy table. This was in a set of notes that Mr. Armstrong did. If you remember, he was pulling in cutout pieces and talking about them. And this is a really, really handy table. So if we go through this real quick, right? A proton, the symbol is kind of a P plus. The neutron is an N0 because it has no charge, and the electron is an E minus. Okay. Location, we should remember that both these, the proton and the neutron, are located in the nucleus, and the electron is surrounding the nucleus in orbitals. Right? Orbitals, those little electron shells. So then our electrical charge, well, protons are +1, neutrons are 0, electrons are -1. Our atomic mass, and we usually do these in AMU, atomic mass units, well, protons are 1, neutrons are 1, and electrons are really, really small, so we call them about 0. It's like adding a penny to a millionaire's bank account. It's not going to make a difference, and especially for the level that we're doing chemistry, it's not going to make a difference for us. Okay, how can we find out how many there are? So how do we know how many protons? Well, the proton is just equal to the atomic number. So we always go to the periodic table, look at the atomic number. That tells us how many protons. Neutrons, how can we find out how many? This we have to do some math. So we have to take our mass number. Now hopefully it's the mass of the specific isotope we have. So if we have like carbon 14, well, our atomic mass is 14, and we subtract our atomic number. Right? So if this was carbon 14, right? To find neutrons, we would do 14, so our atomic mass minus atomic number 6, which would give us 8. So our number of neutrons would be of 8 neutrons. Electrons, to find that without any information, we have to assume the charge is 0, in which case it's the same as the number of protons, which is almost always the case. But if it gives you a charge, right, if it tells you a charge, then you go up and use this kind of equation. You put your charge in, your protons, and if your charge is +2, and you have 8 protons, 8 minus what gives me +2? So 8 minus 6, so I have 6 electrons. Awesome. So we are almost done. Let's just go over a couple things. So isotope, ion, and element. So I like to think about it this way. If I draw a circle like this, and I have element, isotope, and ion, right? I kind of have these different wedges. Okay, an element is when you change and get different elements by changing the number of protons. So number of protons. And so notice there's 3 sections, so we have 3 subatomic particles. This is going to work out well. Right? So an ion is when we have a different number of electrons. And an isotope is when we have a different number of neutrons. So if we change each subatomic particle, we get different things. Change the number of protons, we get a new element. Change the number of neutrons and keep everything else the same, you get an isotope of that element, right? The same element with a different atomic mass. If you keep everything else the same but change the number of electrons, well, now you have an ion. The same element, but it has an overall charge now. Okay, last thing we have a compound, mixture, and element. So remember our POGL that we did, right? A compound is a combination of one or more elements. So it might be a square and a circle and with a triangle on top, right? That might be a compound. Okay, it's a couple different elements chemically bonded together. That's why they're touching, right? Chemically bonded together. An element then would be a substance of just one type of atom. So it could be just a bunch of circles, right? Or it could be like two circles together, right? That's still an element. It's still like, that would be like O2, and that would, like, two oxygen atoms bonded together. And even though they're bonded, since they're both still one single type of atom, we can consider that an element. Okay, and our last one, a mixture. This is like salt water or sugar water. This is where we have some elements mixed in, but it's not just one element. We also have another type of atom in there, but not chemically bonded to the other one. They're just intermingling. They're mixed together, but they're not chemically bonded. That's a mixture. All right, last but not least are our 4 states of matter. So if you remember, I drew a picture in one of our notes, kind of like this. So we had 4 states of matter. We had solid, we had liquid, we had gas, and then we talked a little bit about plasma because it is the most abundant state of matter in the universe, because when we start talking about stars and stuff, they're all plasma. So if we draw a picture of each one, the solids are just, the atoms are real orderly and contained, and the shape, they hold their own shape. The liquids are a little less orderly. They take the shape of their container, but they have a set volume, so it's not like they fill the container, they just take the shape of it, as much volume as they have. The gases are, they don't have a definite shape. They evenly spread out in whatever container they're in, and so it doesn't matter if it's a classroom or a water bottle, it's going to evenly spread out across that, and they're moving all really fast by each other and flying around. And then a plasma looks the same as a gas, but now it's ionized. Now all these things are ions, right? Now they're charged on top of moving all around crazy. And the big thing to remember is, how does our temperature and how does our energy change as we move from solid to gas? So pretty much what it is, to go to a solid, we have to take our temperature down, right? We call it the freezing point. We have to lower our temperature. So we will have a low temperature as a solid, and it goes up, and as we keep raising that temperature, we'll go to a liquid, then to a gas, and eventually we'll get to a plasma. So as we go from solid to plasma, our temperature increases. Now, because when we increase the temperature, we also increase how fast the molecules are moving, right? The kinetic energy of the molecules. Our energy also has to go up. So when they're just vibrating next to each other but not really moving, they have really low energy. And if we could get them to stop moving completely, which is get their temperature to absolute 0 degrees Kelvin, that would mean that their energy is at 0. Right? And we can't physically really do that, but we can get kind of close. And then as we move up to a liquid, they start moving around more, and they start flowing by each other and all that. That means the energy is increasing. We get to a gas, and now they're shooting all around the place, and they're flying around, and they're smacking on the edges of the container. Our energy keeps going up, and then once we ionize them and charge them, we get the highest energy possible. It's important to remember that as we're going to start talking more about this phase change and some chemical structure stuff, and so it's important to have this kind of review in our brain. All right, guys, that is the quick and crazy version of our study guide. I hope it helped out. Remember, you should have more than just my scribbles down. These should just be ways of helping you add on to your parts of your study guide that you already have. I did talk through every single answer, so if you need to, you can go back and slow down and pause and be writing down the things I say to make sure you have every answer on your study guide. You will be able to use this and your notes on the test, so make sure you do a good job and you are ready for the test next class. Like always, if you ever have any questions as you're studying, you can shoot me or Mr. Armstrong a message on Remind, and we'll be more than happy to help. Good luck studying, and I will see you guys on test day. Bye.